So now that we've talked already about what a circuit needs to have in it, what elements are in a circuit, we're going to get more into the details of what's actually happening inside of a circuit, including the variables that we use and the relationships that between those variables that describe the movement of electrons through a circuit. I want to start off by telling you guys what's really happening in a circuit, sort of a scientific description of what's really going on inside there. Little asterisk because there's, details that I'm not going to get into, and some of these things are more complicated than I'm making them look, but at any rate, for freshman physics, this is a good place to start. First thing is that electrons already exist, okay? They're in every atom in the wire and the battery and resistor. I think that there's a misconception that the battery is making electrons, and that's not what's happening. The electrons are already everywhere inside your circuit. Before the battery is plugged in, those electrons are all at a state of equilibrium, which means they're evenly spaced from each other, right? Electrons want to repel other electrons, they're attracted to the protons, so they kind of are spaced out evenly throughout the circuit. And they can move around because everything in a circuit is a conductor, which means that they can move from one atom to another, but then some other electron is going to come in and replace it. When you close the circuit, when you connect the one end of the battery to the other, there's a chemical reaction that happens inside the battery. And that reaction, what it does is it pushes electrons to the negative side of the battery. Now, these electrons are now known as energized because they're all packed together. They're crowded up on the negative side of the battery, and they're sort of unhappy about that. Electrons repel other electrons, so they really would like not to be crowded up, but this chemical reaction is forcing them all to be in the same place. The other side of the battery, of course, is left with an excess of protons because we pulled all the electrons from one side of the battery. So the other side of the battery is positive. The battery actually becomes polarized. And that positive side of the battery is really attractive to those electrons, but they can't go backwards through the battery because that's the way the chemical reaction works. So they'd like to get back to the other side of the battery, but they can't move directly through the battery. So when we close that switch and there's a conductive path consisting of resistors and wires that connect the negative side and the positive side, the electrons flow through that circuit to try to get back to the other side of the battery. When the electrons go through the resistors, those energized electrons give up some or all of their extra energy. So they started off sort of at a state of equilibrium. They got energy when the chemical reaction in the battery started happening, and they give up that energy as they're passing through the resistors. And those resistors take that electrical energy and they transform it into other types of energy like heat, sound, or magnetism. As I referenced in the last video, I think it's really useful to use an analogy, which is kind of like a story that helps you to make educated guesses about what's going to happen in a circuit. And the analogy I like to use is that a school day is like a circuit. So in this analogy, the students in your school day are like the electrons, and it's their job to move through the day, right? The students don't pop in and out of existence. They're already there. You're already in existence. You just move throughout the school day. Your home is like the battery. This is the place where you get your energy. You eat a good healthy breakfast in the morning before you leave to school. So it gives you your energy at the very beginning of your school day. As you move through the school day, the hallways are like the wires that you're passing through. They're pathways for students to get from place to place. And as I mentioned in the last show, the length of those wires is not relevant, right? You got to get to your class regardless of how far you have to walk to get there. The length of the wires doesn't make a difference. An exam or a test is like a resistor. It's the location where you should use up your energy. So you get energy in the morning, and then as you move through the school day, you run into a series of tests, and that's where you're going to use that nice energy that you took from home, and you're going to transform it into something useful, like, for example, a good grade. To describe what's really happening in the circuit, it's useful to have some circuit variables. We're going to use 4 different variables to describe what's going on inside our circuit. You've probably heard most of these words in the past, but we're now going to be attaching some real scientific meaning to those words, so it's useful to really pay attention here. I also should tell you that you will have a quiz on this. This is one of the very few quizzes that I give you all year long, but I'm going to have a quiz on what these variables are and their units. So you should take good notes here and maybe even make flashcards. There's an example problem at the end of every slide that is sort of what you will expect to see when you take the quiz. So the first circuit variable is known as voltage. We use a capital V to represent voltage. And voltage is defined as the amount of energy in each electron. So if you think back to your school day analogy, it's going to be basically the amount of energy each kid starts the day with, or the amount of energy each kid uses up at a specific test. The units of voltage should go along with that definition, right? Joule is the unit for energy, and Coulomb tells me how many electrons I have. So the unit is going to be joules per Coulomb. There is a shortcut for that. It's known as the volt. So the kind of problem you might expect to see on a test or on a quiz would say just a statement like the battery gives off 60 joules of energy to 4 coulombs of electrons that are passing through. So if you remember that voltage is the amount of energy in each electron, you should be able to use that information to figure out that the voltage is 60 joules divided by 4, or 15 joules per coulomb. So each electron has 15 joules if the total was 60. Another way to write this would be 15 volts. So V is equal to 15 volts. The second circuit variable is known as current, and we use a capital I to represent current for no good reason that I can think of, but it is what it is. So current is an I, and current is defined as the number of electrons each second that pass through a device. So either pass through the battery, or pass through one of your resistors, or pass through a switch. How many electrons every second are going through. The unit for current is going to make a lot of sense if you consider the definition. The unit is coulombs per second, so number of electrons every second. And we do have a shortcut for that. It's known as an ampere, which is sometimes abbreviated amp, or even just plain old A. A question on a test about current might say, in 120 seconds, 30 coulombs of electrons pass through a resistor. So if you remember that current is defined as the number of electrons every second, you know there's 30 electrons in 120 seconds, which means that the current is going to be 0.25 coulombs per second, or 0.25 amps. The third circuit variable is known as resistance, and it's going to be a capital R. Of course, it shouldn't surprise you that resistance usually has to do with the resistors in the circuit, and it's defined as how difficult it is for the electrons to pass through a part of the circuit. So a resistor that makes it really tough for the electrons to pass through is going to have a high resistance, and a resistor that doesn't really make it too hard for those electrons to go through will have a low resistance. The units of resistance are super ugly and probably aren't going to make a lot of sense, but it's a joule second per coulomb squared. Don't remember that. Instead, we'll call the units for resistance the ohm. That's a shortcut for that. So the thing about ohm is it's drawn as looks like a little horseshoe. It's the Greek letter omega, and that's what the standard unit for resistance is. Example problem for resistance, something like this. A 4 ohm toaster and a 1 ohm coffee maker are in a circuit. Which one of those has more resistance? Well, the toaster. It has 4 times as much resistance as the coffee maker, which means that it's 4 times more difficult for the electrons to get through. So I saved the most important variable for last, and as we start using these variables in equations and solving for some values that are happening in circuits, you'll realize why this is so important. So the fourth circuit variable is power, which we've actually learned about in our last unit. Just like it was with the last unit, power is defined as the total energy transformed every second. In other words, the work every second. And just like the last unit, the units are going to be joules per second, otherwise known as the watt. So you might get an example problem that says something like, in 30 seconds, a light transforms 90 joules of energy into light. And that would mean that the power would be 3 joules per second, right? It's the amount of energy every second. So 3 joules every second. otherwise known as 3 watts. Quick summary of this slideshow. 4 main circuit variables describe what's going to happen to the movement of electrons and the energy in a circuit. The variables are a little bit tricky, right? They kind of are made up of the same fundamental things. There's energy, there's electrons, and there's time, but the specific combination of those variables determines the specific circuit variable that we use. So I would really recommend making flashcards about these and working on them until you can quickly give the definitions of each variable and the unit.